Welcome to Innovate and React. In today's episode, we will be talking about the HSAB concept. I'm sure every chemist has come across this concept at least once and maybe even used it to predict the outcome of reactions. However, the HSAB concept might not be as complete as we think, and there are different methods to better predict the outcome of reactions by using nucleophilicity. And today I'm talking to Justus Reitz, who is also studying at TU Dortmund University. Maybe introduce yourself a bit.
Hey Kevin, thanks for having me. I have studied chemistry at the TU Dortmund and did my PhD studies in the group of Professor Hansmann in the organic chemistry. And during my PhD studies, I dealt with unstable or at least very highly reactive molecules and how to basically stabilize them, how to use them in reactions, and also I had nice collaboration projects with, for example, a group in Munich which researches nucleophilicity in molecules. And there we had collaboration projects to really determine nucleophilicities and how you can control this.
And what is the main concept to describe this? From what I think all chemistry students learn, this HSAB concept is one of the methods of describing how nucleophiles and electrophiles interact with each other.
Yeah, they are the group in Munich which I had the collaboration with is the Mayr group, or also now the Ophir group. Mayr was the one who developed the scale of nucleophilicity, so really giving nucleophiles value to measure their strength and determine how fast they basically can react with electrophiles, and if they can react with electrophiles at least at a sensible rate. And this was developed by Mayr, and Ophir took this now over after Mayr retired. And the HSAB concept, the Mayr group had a paper about in 2011 discussing that the HSAB treatment of these ambident nucleophiles, so nucleophiles with two reaction sites, and determining which site would react with electrophiles given on whether there is a hard site, so small and high charged, or a soft site, so bigger electron density distribution basically. And
what are examples for that? For a hard base, for example?
It's often explained with metals, where you can imagine this very easily, like gold 3 plus gold 1 plus, with gold 3 plus being the softer Lewis acid basically, or being the soft electrophile in this case. So basically just higher charge and smaller ion radius. And of course in organic chemistry you can also talk about this. For example, strong nucleophiles which are organic that are used on a daily basis in labs are, for example, triphenylphosphine or something. And they are just values can be given with relation to a standard. And there were already attempts before Mayr did this to make a general nucleophilicity scale. And they were referenced, for example, to methyl bromide and as a standard electrophile and so on with a value 1, and then you just give different values depending on just how fast a nucleophile reacts with this and so on.
So you have a standard, and then you throw different electrophiles on it, and then you compare that with different nucleophiles, and the speed can then be, okay, this is faster than this, so it's in the scale higher. But there are no distinct values that you can measure?
You measure distinct values, but basically to have a comparability, to have useful number values. I mean, if just, for example, nucleophile A reacts with electrophile B, and you give a reaction rate, this is not really useful in everyday chemistry. And to make this useful as a really value number, they made this in relation to other nucleophiles. So they have nucleophile A has a value of 1, nucleophile B has a value of 2, and so on. And so it's a logarithmic scale. So the higher the value, the much stronger the nucleophile is and reacts. To have this useful as a tool in organic synthesis, you have basically a nucleophile with a value of 5, reacts in a fast manner, so seconds to minutes, with a electrophile with a value of -5. So basically you just compare values, and if the values are similar, you will get a reaction that is in controlled manner, but in a quick and good time scale. This actually where the critical point of the Mayr scale is. You have nucleophiles just arranged by their strength, and so you can just see if an electrophile already got characterized or if a nucleophile already got characterized. You can already see, do they react with each other, and do they react so in a good, timely manner? As a chemist, you don't want to wait for a reaction for a month to finish. But also, it cannot react too fast, because otherwise you are in the time limit of the diffusion range, basically. And diffusion time limit range always means you have a loss of selectivity.
To determine in selectivity, if you have two sites, and then you want to use these values to predict which site is attacked by the nucleophile.
Yes. So there, in the diffusion range, you basically don't have control over. Because diffusion range means basically you don't have a kinetic barrier, meaning as soon as two molecules meet, preferably they react, and not just at one site specifically. And so that the Mayr group, or also now the Ophir group, could do this whole nucleophilicity scale means one very simple thing. The whole HSAB concept, and this also they described as a paper, as I mentioned, is just, well, not really usable. It is not sensible to use. And a lot of chemists in their studies, and also a lot of organic books in chemistry, still talk about the HSAB concept as a concept you can refer to. You look at an ambident nucleophile like a cyanide ion, and then you can say, okay, the cyanide ion will react with hard electrophiles with a nitrogen side, and with soft electrophiles with a carbon side, because you have in the cyanide ion you have the electron-rich nitrogen, which would be the hard side according to the HSAB concept, and you have the softer side with the carbon atom. And according to the HSAB concept, depending on the electrophile, whether you have a hard electrophile or a soft electrophile, you would either get a nitrogen attack or a carbon attack. Now, the nucleophilicity of the Mayr scale has one nucleophile strength for each nucleophile, saying this concept should not exist if the Mayr scale is really valid.
The concept of that it has two.
The concept of HSAB, that you can basically choose an electrophile. It reacts with the nucleophile reacts with the electrophile, depending on the nucleophile side, whether the electrophile is hard or soft. So this whole HSAB concept by Pearson that was developed is just not a concept you can use because it is not valid. This is the claim that the Mayr group did. And they also have, they have good reasons for this, because if you look into literature and if you also look at the examples and so on, you can actually see that the HSAB concept doesn't hold true as a predictive tool. As a predictive tool, it would be very strong in organic chemistry, because you could actually use this for reactions and can say, if I design my nucleophile differently, I can use this as a tool to construct molecules, but actually it just does not hold true.
I think the good part, or the why it is so appealing to use this concept, is because it is relatively easy to just look at the molecule and then see if this is a hard or a soft nucleophile or acid, and you don't need to go to the lab and measure stuff from theory. Obviously, you have to then validate it, and that's where the limits came out. But as a concept, it's very appealing to just look at the molecules and be like, okay, this should react with this, and then we go to the lab.
Totally.
Oh.
I mean, that's also why it's used and taught. I mean, a lot of students, and as I said, also nowadays, up-to-date, newly coming out organic chemistry books still sell the HSAB concept as something that is of high value and that helps you predict reaction outcomes. But, well, it just doesn't work out as it is explained, because this whole concept was designed somewhere in the 1960s, I think 68 or something, by Pearson. And of course, there were also predecessors like Kornblum's rule, which stated that depending on the transition state, you can determine the reaction outcome and so on. And of course, there's always some sense to it. And that's also why it's so nice, because if you can break down a model to really, really simple things and it still holds true, that's what, well, chemists are looking for with every model for explaining students how chemistry works.
Exactly.
But the problem is that basically all the examples that were made to prove the HSAB concept are either in the diffusion limit range, so you actually get also the other attacking product, not because the HSAB concept holds true, but you basically always get mixtures in these cases, or you can just in the other case, isolate kinetic products. So it's not about the site, hard and soft. It's about thermodynamic or kinetic control of the reaction. And so this claim that is made that the HSAB concept, hard reacts with hard and soft reacts with soft, well, could just not be proven, or more or less it could be proven wrong by the Ophir group.
Yeah, all the models we use to explain what happens in chemistry are always not like the exact reality. They always just show or make the reactions more visible, and these models just hold up until someone proves them wrong, and then we have a new model, in this case then this Mayr scale, which categorizes the electrophiles and gives them values how fast they react with the nucleophiles?
Well, they start basically with the nucleophiles. So there are over 1,000 nucleophiles, I think, now sorted in this, and about, I would need to look up the numbers, I think 200, 300 electrophiles or something. So the nucleophile as the main reacting species is the focus on this. It also got a nickname of, or it is more the principle of the constant selectivity relationship. So you basically have a nucleophile, it has a reacting site and it has a strength. And either it reacts with an electrophile or it doesn't react with the electrophile, depending on whether it's strong or whether it's weak or whatever. But it does not react on two different sites depending on, so the nucleophile doesn't react with two different sides of the atom of the molecule just because, just because the electrophile behaves differently. But so it has one reactive site, and you can control still kinetic and thermodynamic or something, but you cannot have two different thermodynamic outcomes just because you have a different electrophile.
So it really focuses on if the reaction happens, but you can still also apply kinetic control to the reaction when
I mean, this is simply another chemistry model, whether you have a thermodynamic reaction or a kinetic determined reaction. This is something completely different from that, but that's also one of the problems of the HSAB concept. The HSAB concept never spoke about kinetic or thermodynamic control or something like this. It just stated very simply, and also again in relation to Kornblum's rule basically, that you have different interactions based on hard and soft, and also like orbital control versus Coulomb control and so on, but you basically have different points of interaction depending on both reaction partners. And this is just as a general rule and as a concept you can use to predict reaction outcomes, just not usable.
Yeah, but now also with this Mayr scale, where they actually have measured all these nucleophiles and then give a strength to it, you can relatively easy. I've been on their website. You can just look up molecules and then see how strong they are. I guess also you could guess from one molecule to another if they're very similar, but not the exact molecules in the scale, that you could say, okay, they should have a similar.
Yeah,
and
definitely.
principally cover much more than there is, but there are already a lot of molecules.
Yeah, that definitely. I mean, of course, you always have different factors determining nucleophilicity and so on, but then you also always can really look at the basics of nucleophilicity, like what is nucleophilicity determined by, and that is very simple. Do you have electron pushing groups? Do you have a reaction center that is freely available, so no steric hindrance? Do you have an alpha effect, so directly attached to the nucleophilic atom? Do you have an atom attached that can donate a pi electron pair or something like this? And so you can always think about similar molecules and then argue, okay, this is not measured, but this could have a stronger or a little bit weaker nucleophilicity, but it should be in this range. And that's why I think the nucleophilicity scale as a tool for chemists can be actually very strong.
Do you have maybe some examples from your research when you use the scale to determine the outcome of a reaction, or?
So actually not to determine the outcome of a reaction, but in my case, so I dealt with the unstable molecules and how to make them stable and so on during my PhD. And the Huntsman group had the, also luck, but we were able to show the stabilization of a new functional group in organic chemistry. And this doesn't happen every day anymore.
That's rare.
Most functional groups are already known, but in 2021 we were the first ones to report stable diazoalkenes. Diazoalkenes, so basically just CN2 moieties, are known for, I think, 1880 or something like this. So they are known for over 100 years and well-established group with reactivity explored in everything. Diazoalkenes, so just the higher homolog, C and 2. Well, they have been proposed as intermediates in a lot of organic reactions actually, and they are potentially a useful group also to use as an organic chemist. But up to 1980, 1990, something like this, they couldn't even be proven in matrix isolation studies. And matrix isolation studies are studies that basically try to isolate really single molecules in a frozen argon matrix. So molecules at around 5 Kelvin, 3 Kelvin, 10 Kelvin, depends on the reactions. But you really try to deposit molecules single-handedly by vacuum methods onto a surface and then try to cool them down to very, very low temperatures.
So they don't move anymore, and there's not enough energy in the system that they react with anything, and then you can...
Exactly. And they are completely singled out, so they also cannot dimerize easily or whatsoever. Well, that is the ideal theory behind this, but so you can really research the most highly reactive intermediates and whatnot. But up to this point, actually, even, attempts to study diazoalkenes in this method didn't work.
Because they were too reactive, and even at this low temperature they did something.
So they started to intramolecular stuff, and even at these temperatures, you have to imagine even this is difficult for molecules to do, because you still have to have degrees of freedom in rotation and so on. And this, matrix isolation is for suppressing these things, but it took until then to prove the first diazoalkene, which, in the matrix isolation study was impossible, but you couldn't stabilize them. And then in 2021, we were able to, synthesize the first that are stable even at room temperature and solution and even over days.
Okay, and how could you stabilize them? With the construction of the molecule, that only certain diazoalkenes are stable, or did you have a method to actually stabilize all of them?
first it was just a lucky shot, but basically it was done with super strong nucleophiles. And this was done with the reaction of N2O with this super strong nucleophile, so, well, nitrous oxide, laughing gas. The thing about these super strong nucleophiles is that N2O is normally a rather inert gas, or if it reacts, it is known to react basically under N2 release. So it oxidizes stuff, N2 is released, and this is, of course, thermodynamically super much favored. But these very, very strong nucleophiles, they are called mesoionic and heterocyclic olefins, but it's basically just a polarization of a carbon atom so far that it basically has an anion character, more or less. And this could then react with N2O in a fashion that it attacks the nitrogen atom of N2O.
And then there is no nitrogen release in the reaction, because that's
exactly the covalent bond formation point. And so in the end, actually water is just released in a multiple step reaction process. But you had the ability here to use these super strong nucleophiles, and that's why I didn't use in my PhD this nucleophilicity scale to predict outcomes, but we actually tried to then manipulate a little bit or try out how strong does a nucleophile really need to be. We worked there with the OFIA group now to get in collaboration to determine the nucleophilicities and so on. And then we just, took less and less nucleophilic molecules to see how strong does a nucleophile have to be to react with N2O. And then also, why is the diazoalkene stable? Well, actually they are stable as a group because the precursors, the reagents, these mesoionic olefins, donate super much electron density into the CN2 fragment, into this diazoalkene fragment, so that it's actually stably bound to the rest of the molecule. And the lower you go in electron density that is pushed into this fragment, the more unstable this becomes. And so we actually played around with this nucleophilicity scale and really had values we could attend to of different olefins where we could see, okay, this gets less and less stable because less electron density is pushed into the fragment.
The more nucleophilic a compound is, the more electron it gives to the molecule, and the more electron density you have in this molecule, the more stable it becomes.
Yeah.
So when you have lower and lower nucleophilic strength, then you have lower and lower electron donation to this reaction, and then it becomes less stable.
Well, you cannot use this as a general concept, just push electron density into something and then it becomes more stable. But in the case of the diazoalkenes, we could see that, basically this holds true as a general rule of thumb, basically. But this is also due to the electronic situation of the diazoalkenes. Diazoalkenes are unstable generally as a group because they are very easy also to lose nitrogen. So dinitrogen elimination again to build a diradical. And there it's a little bit more complicated again about singlet and triplet state, which we studied then also. And basically...
Of the radicals.
Yes, exactly. If you push more electron density into this fragment, instead of the singlet state of the unstable diazoalkenes, you get suddenly a triplet state. And there you can see that basically just the nucleophilicity of the precursor, you could say, but in general, just the electron donating residue you put to your functional group stabilizes this molecule and stabilizes the N2 loss, that these molecules don't just lose N2 because it's so thermodynamically favored. If the question if there is an electron poor diazoalkene is another question, and probably not, but maybe there's a way to stabilize them, but this we didn't manage so far. We just could see we just could see that basically the more nucleophilic the precursor is, so the more electron density it is able to donate, the more stable is the diazoalkene.
So that's why you then explored the upper range of this Mayr scale of the nucleophiles.
Yeah, actually this was a lot of fun, but they're really just basic concepts of chemistry can be seen, because we, after designing these MNHOs, these olefins, we basically tried to see how much can we push this bar, because with the MNHOs we could already see they are super strong nucleophilic in qualitative experiments. We could see they are more nucleophilic, for example, than NHCs, than the for just basic chemists also known these heterocyclic carbenes. But these more niche functional route of the heterocyclic olefins, and also then the mesoionic olefins, which are even more polarized, there is not much known about this. And then we wanted to see what types of influence can we use to really push the electron density on this fragment, and so thus also the nucleophilicity on the carbon atom as a nucleophilic center, and also how far can we go. And this how far can we go was then actually very funny, because it is now the strongest nucleophile reported up to date. So the strongest nucleophile known is a mesoionic olefin that I designed during my PhD, which was very fun.
That sounds pretty amazing, especially when you have a new functional group to work with, and then because of that you see, okay, what else is possible, and then to test this new functional group you also push the limits of this nucleophilic scale. That sounds very interesting. There are probably not directly applications of this chemistry yet, I assume, but pushing the basic research in this field is then basically gives a whole new branch of chemistry in this, or with the functional group you could do a lot and it's not known yet.
Yeah, so of course direct applications is always tricky with things like this, because this is basic research really of basic concepts and of what can we actually do, not with the main focus on what can we use it for. And so I would say, of course, if you have a new functional group in organic chemistry, that's very, very useful, because you can have, again, basically an additional tool as an organic chemist to design molecules and how to construct molecules. But even if you apply this to unstable diazoalkenes, because we were able to isolate diazoalkenes and research the reactivity and so on, we could really just much more focused and much more controlled see and isolate the products of reactions of diazoalkenes with some educts. And so we could see that diazoalkenes with carbon monoxide react to the ketenes and so on. So just reactions that were before not really able to do this in controlled manner and so on, we could now see and reacted with different electrophiles what the outcome is. And if you now would synthesize unstable diazoalkenes, you could maybe use this as a tool in your reaction set, so you don't even need to use these very special stabilized diazoalkenes, but you can use this as a general tool.
Yeah, because you learned from the stable ones, there are not that many, but because they are stable, you can look into the reactions much better, understand how this functional group works, and then you have these unstable ones, which were previously just they might be there as a transition state, but could not really be proven. And now where you predict that this diazoalkene will be as a transition state, you can use what you learned from the stable ones to predict what happens with these, or at least understand better how these transition steps work.
Yeah, exactly. And thus, for example, one of the projects that was really cool was also we were able to, in cooperation with the Kasamanchev group, also at the TU Dortmund, but they have an EPR spectrum. So basically they could research this triplet species that results after the N2 loss if you irradiate it with light. And they researched this species and could see the first triplet vinylidene formed. So the first CC fragment where there's a diradical in the triplet state. And so because of this basic research, we were able to analyze, characterize, and also a little bit play around with species that were before not known and also could not be characterized because of the instability. And thus, this basic research doesn't have a direct focus on application. It also doesn't have any direct connection right now, but there's some basic research that can be built upon.
Yeah. And it pushes the models that we know to a limit and helps to refine these models to make them more generally applicable. And yeah, it's really interesting when you go really so deep into the basics of chemistry that you still can find new stuff. And it's not, we have researched chemistry for so many years that now all the basic concepts are known and we just have to find new applications. No, we actually can still find new functional groups, new models. That's pretty amazing.
Yeah, actually, I think that's the whole base or the whole reason for basic chemistry or basic research, why this is still important and why this should still be also focused on, and not only directly with a focus on applications, but can we push this further? Can we actually do something here? And of course, in the eyes of application-focused chemists or application-focused people, this is maybe a little bit just playing around and with no real target or so on. And in my eyes,
yes, that's the thing, that it will eventually, someone, once this concept is established, someone will use it in a different way, because they are not focused on how stuff works. They are then focused on, okay, we have this new concept now, how can we apply it? But to apply it, first we have to understand how it works, and that's why we need this kind of research. Yeah, definitely. When you see more, then you can look into new stuff that was just not possible to see anymore, I think. Before the electron was discovered, and this is just like, that's very drastic finding, but before that, it was also not known that there are smaller particles, and then this opened basically up the whole research about also in chemistry on how these electrons are placed in the molecules and how they are basically the way how molecules interact.
Yeah, and of course you cannot make every day these groundbreaking discoveries, which is a little bit sad. But for example, for the nucleophilicity measurements that I did together with the OFAIR group and so on, it was also actually still some papers you can find where it states the nucleophilicity can be just correlated, for example, to the proton affinity or something like this. And proton affinities you can really easy calculate.
Proton affinity means how well they react with protons?
Basically it's how well you can take up a proton, or a little bit simpler expressed, the basicity. It's not exactly the same, but basically a lot of papers still state you can correlate the nucleophilicity and the basicity of molecules. And while this holds true for simpler molecules and can give you a general idea maybe, this is just it's not a general correlation, because the big difference between a general electrophile and a proton is that a proton is super small and the orbital situation is super easy to understand. For electrophiles, this is completely different, because electrophiles then have an electrophilic center. In organic chemistry, of course, a lot of carbon electrophilic centers, but these have different geometries, these have different energy values, generally speaking. And so if you are attacking this, also the reorganization during the process takes a lot of influence on the whole energetic profile of the reaction. And so, for example, just researching these MNHOs and how you can influence the nucleophilicity in these systems gives you a good understanding of how you can influence nucleophilicity, also generally speaking, more broadly on the on the heterocyclic core. And if you now just say the nucleophilicity can be correlated to the proton affinity, this is just a rough measure that will fail if you really look for designing specifically heterocycles with different electron density distributions.
Why?
Really easily speaking, if you have the carbon atom as a nucleophile attacking a proton, the proton will not reorganize its structure because it's just one atom. And also, it doesn't matter which nucleophile you have, the proton will always be just a simple s orbital thing where you attack into. And if you are talking about the electrophiles like carbon electrophiles, nitrogen electrophiles, maybe or something like this, like imines or something, it's very, very simple. You have an electrophilic core, but of course you have molecular orbitals. And you have molecular structures of these electrophiles. And if now the nucleophile attacks, you have a reorganization of the whole molecule. And you have steric hindrance in these partners and so on. And you have orbital overlaps that first need to happen for the reaction for the covalent bond to form. And
they have to match previously so that you cannot react any orbital with any orbital. But when there's only one,
reacting with a proton is no problem, and you basically cannot make steric hindrance arguments or whatever. And this, we could also see steric hindrance is a big factor in nucleophilicity. How well, or in some cases, then how badly your reaction center is really protected by or shielded by other organic rests or something, hinders, of course, the reaction. And so the nucleophilicity will grow lower and lower because, how do you stabilize some very reactive intermediates? Just put a lot of bulk around them.
Yeah. So it's like when you use diisopropyl amide, where it is a nucleophile, but because of its shielding, it basically can only react as a nucleophile. No, it's a strong...
As a base.
Yeah, as a base, yeah. No,
but
I mixed this up, but it's the other way around, right?
Yeah, but actually, exactly. This is a very important point generally also in organic chemistry, why you have a non-nucleophilic strong bases. Because sometimes you really just want the base character, you just want a reaction where you remove a proton. But if you at the same time have a nucleophile, a lot of electrophiles can also, of course, so they cannot only react as electrophiles, they can also react as acids.
But that was that also a problem with your compounds? From what I remember, they were also strong nucleophiles, but don't really react as bases.
Oh, they are super strong bases. That definitely, they are super strong bases. But that's one of the parts why they are, for example, air sensitive. In air, they immediately react with water and also oxygen, for that matter. Basically, the separation of nucleophilicity and basicity is very important because you need to know when this is a super strong base. And calculating proton affinities is super easy. You cannot say, okay, this is a strong nucleophile, and you can also not say, is this a stronger nucleophile or is this a stronger base, which reacts first, and so on. Of course, if it has a high basicity, the reaction with protons is always just kinetically very preferred, just because a proton is so small and can just transport much faster and so on. But that's also why we then did calculations with methyl cation affinities. And a methyl cation, just a CH3+, still a very simple molecule and still for nowadays computers relatively easy to calculate the reaction between any nucleophile and the methyl cation. The methyl cation affinities you can actually much more closely correlate to the nucleophilicities, while the proton affinities fail there.
Oh, okay.
But so doing these studies, seeing how we can influence the nucleophilicity, we then also try to apply this for computational methods, and there we could see the correlation to the proton affinities fails, while a simple calculation of the methyl cation affinities gives you very good picture actually of what the nucleophilicities should be.
Mm-hmm. Yeah, that's also a good point, that you have to see how these different concepts then work. Maybe one question in a different direction. So when you started with your research and you had this very new functional group, how did you start with, like, did you just want to play around with it and see what happens, or what was the target when you started? I know that in the PhD sometimes you have a plan in the beginning and then you just at some point go in a completely different directions. How was this with your PhD?
I had actually a completely different plan for the PhD because I started in the group. Then we discovered the diazoalkenes, but actually it was not me on the project who discovered this, but a fellow PhD colleague. And then I basically took over this topic. And we started investigations basically by, first of all, what's known about diazoalkenes. So diazoalkenes are, known is difficult, but they were at least postulated in a lot of reactions. And so, of course, you have a look, they are postulated here. Can we use this and can we see the same reactivity? Can we really talk about these postulated diazoalkenes in the same way we can talk about our stable diazoalkenes? This was one of the first steps. Then you, of course, look for, you have a novel functional group that seems to be very energy rich, because still we are talking about a molecule that can easily activate stuff that we can. So the mesoionic olefins, the precursors, have a very high nucleophilicity, and the diazoalkenes should have still a high nucleophilicity at least. This we also research, but this is not published now, but they are very, very strong nucleophiles. And basically what we did was, on the one hand, see similarities between postulated diazoalkenes and our diazoalkenes, but also we had a look, diazoalkenes, the homologue, has known reactivity. And they are, of course, that's also one of the first examples that was, of course, tried, is diazoalkenes are known if you radiate them with wavelength 400, 350 nanometers, something like this, or whatever, they lose N2. Can we do the same with the diazoalkenes? Yes, of course we can. And what happens, and so on. So the first thing you start from is mostly things that are closely known.
And then you try to apply these concepts and see if they still work. And if not, why not?
If they still work. And also, of course, diazoalkenes were not stable before this. And then can we get to other closely related molecules that are not stable, and are they also then somehow stable with the approach we chose, and so on? And there we also could see a lot of very interesting stuff. But
very interesting. It's a topic where you have to really emphasize your curiosity and just go more deeply into this chemistry. Very interesting. Thank you for the talk, and it was very interesting to learn about these very basic concepts.
Thank you for giving me the chance to talk here about my chemistry, and it was nice.
If you liked this episode, please consider following on wherever you're listening to this podcast. Also, you can find out more on innovateandreact.com. There you can find all the episodes and additional information. If you have an interesting topic that you would like to share with the audience, contact me via email, contact@innovateandreact.com, or find me as Kevin Hares on LinkedIn. Thank you so much for listening, and stay curious.